Hey there, Calc 2 crew, and welcome back to the Daily Problem Sets. All right, let's go ahead and venture on into Chapter 10. Let's start by talking about parametric equations. So here we have x and y are both represented as a function of t, and we'll take a look at some examples. First, I want to consider the following equations. I have x as 1 minus t squared and y is t minus 4, and that t goes from negative 2 to 2. We'd like to sketch the curve by using the parametric equations to plot points. We'd like to indicate with an arrow or an arrowhead the direction in which the curve is traced as t increases. And then at the end, we're going to try to eliminate the parameter to find a Cartesian equation for the curve. So right away to start, I'm going to actually set up a table. And I'll start with t values. But then for each t value, I should be able to solve for x, where x is 1 minus t squared. And I should be able to solve for y, where y is t minus 4. And I could really pick t values as I see fit, but I want to keep in mind that t is from negative 2 to 2. I'm just going to use integers then. So I'll say if t goes from negative 2 to 2, I'm going to use negative 2, negative 1. We'll do 0, positive 1, positive 2. And this should hopefully be enough to give us reasonable information to work with. My table, building my table. Something about building a table by hand. It's really nice. Like we're in shop class. Let's plug negative 2 in for t. And here, we'll do all the x first and then all the y. So if I plug negative 2 in for t, I get x is 1 minus negative 2 squared. So that's 1 minus 4 gives me negative 3 for x. If I plug negative 1 in for t, I get 1 minus negative 1 squared, which is 1 minus 1, which gives me 0. If I plug 0 in for t to find x, I get 1 minus 0 squared, which is 1 minus 0, which gives me positive 1. If I plug positive 1 and positive 2 in, these should look familiar. Since I'm squaring whatever I plug in for t, the sign shouldn't make a difference if it's the same number in magnitude. If I plug positive 1 in, I get 1 minus 1 squared, that's 1 minus 1, equals 0. If I plug 2 in, positive 2, I get 1 minus positive 2 squared, which is that familiar 1 minus 4, gives me negative 3. So I have all of these x values. Let me circle them just so they're easy to spot. I'm going to box 0 because 0 already kind of looks like a circle. But you know what I'm saying. You know what I'm doing. Now I'm going to plug in my t values to find y. So if I plug negative 2 in, I get y is negative 2 minus 4, and that's going to give me negative 6. If I plug negative 1 in, I get negative 1 minus 4 gives me negative 5. We can maybe notice that y is going to move linearly, so at some point it becomes kind of predictable. If I plug in 0, I get 0 minus 4 gives me negative 4. If I plug in 1, I get 1 minus 4 gives me negative 3. And lastly, if I plug 2 in for t to solve for y, I get 2 minus 4 gives me negative 2. So here I have these ordered pairs. And I want to think of them as ordered pairs. Once I have the table, I don't really need to consider what's going on with t anymore. I can actually think of these as ordered pairs x comma y. So I have point negative 3, negative 6, 0, negative 5, 1, negative 4, 0, negative 3, and negative 3, negative 2. And I'd like to get some visualization for how this is going to look. So here I'm going to go ahead and get my graph paper, my homemade graph paper. Here we have the x and the y axes, and we'll get some grid here. Y is going to go as far down as negative 6, so I want to keep that in mind. Negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. And it looks like x is mostly in the negative direction. So we'll do negative 1, negative 2, negative 3, negative 4, something like this. And let's start plotting points. So the first ordered pair I have when x is negative 3, y is negative 6. So negative 3, negative 6. somewhere in this vicinity. Then I have x is 0, y is -5. So that's right on the y-axis. I can plot that point. We have x is 1, so I didn't put a little notch there. Well, let me go back and do it. I think it's worth doing it. There we go. Back to the baby blue. When x is 1, we get y is -4. We can plot that point. Then back to x is 0, but now y is -3. I can plot that point. And then x is -3 again, but y is -2. So I can do my best plotting that. Now when I go to sort of graph this, and this one should actually be centered, I think, a bit better over this one, but it's just a rough sketch. I think a tendency is just to connect with a smooth curve through the points and to leave some overhang. However, there's a restriction on t. That t was just between -2 and 2. So these points that I started and ended with should actually be considered initial and terminal points for the curve. So I'm going to try to avoid that tendency to kind of run through them all. So I'll start at this first point, connect with a smooth curve, try to get an idea as to how this parametric curve looks. And I want to use arrowheads to indicate the direction. So that point that I started with, that very first point that I plotted, was for the smallest value of t, and I kept plotting points as t increases, so the order in which I plotted the points is the direction that the curve should be going. So we use little arrowheads to show this as a direction, how we should be sort of traversing on the curve. And so this gives us our parametric curve that we're working with. And we can see that there is some indicated direction. That's something that's a bit unique to these parametric curves, because we're going to see now that I could eliminate the new parameter t and get something that resembles something more Cartesian, something we'd be used to. But what's nice about the parametric curves is there is sort of an indicated direction that we should be traveling in. So we did this. Now I want to eliminate the parameter to find a Cartesian equation of the curve. We had x is 1 minus t squared. And y was t minus 4, right? Y was t minus 4, and that's from -2 to 2. The restriction that we placed on t that was given. Now here, when I want to sort of eliminate parameter t, I'm really looking to get a substitution if at all possible. And one of these equations is actually going to be easier to work with. I'm really thinking about working with y, because I don't have to do anything like taking a square root. Taking a square root can always be somewhat risky business. But if I go to the second equation and solve for t, we would say, well, then t is equal to y plus 4. And I can use this as a substitution statement into this first equation and say, well, then x is equal to 1 minus, instead of t squared, it would be y plus 4 squared. And you could FOIL this out, distribute the minus sign through, and sort of claim that that's a nicer way to present the final answer. But I think this is great just as it is. Here we have x as a function of y, which is likely what we would expect given the sort of interesting orientation of the parabola that we have here. But there's another thing we want to mention, another thing I should mention here. When I look at this, since I do have x as a function of y is my input, y is my independent variable. That's what I'm plugging in, and x is the output. So a bit of a role reversal than what we're used to with traditional functions, but no harm, no foul there. What I want to do, since my parametric equation had a restriction on t, and t was the input, now that I've eliminated that parameter, I don't want to eliminate the restriction. So I should be thinking about y is my input, and I should be placing some restriction on y. And if it helps, we can actually look at the table. We saw that y is just going, it's moving in a very linear fashion between -6 and -2. And that's in fact the restriction I want to give, is that y should be between -6 and -2. Because it's not going to be all of this Cartesian curve, it's just a piece of it, right? I said I don't want to draw it all the way through and continuing on indefinitely. I want to honor that restriction. So here I'd say, well, it is the curve given by this equation, but not forever. It's got a restriction, and that y only goes from -6 to -2. This is a great way to put it. Let's take a look at one more example here. So I want to consider the parametric equation, and let me actually change this just a little bit. Let's make this, so it's a bit more interesting, let's make this x equals square root of t and y equals 3 minus t. So we're going rogue here. So we'll make this a square root of t. And so what I'd like to do now is I'd like to go ahead and essentially do the same stuff. I want to build out my table. I want to get a sketch. I want an arrowhead to indicate the direction. Then I want to try to eliminate the parameter. So here I'll pick values for t. I want to plug into x, and we changed x to make the problem a bit more interesting. X is square root of t. And we have y is 3 minus t. And here, I can sort of pick whatever values I want for t. We want to stick in the real number system. So we'd say, well, don't pick anything negative. Anything negative under the square root's not going to be good. But otherwise, I'm going to let x dictate the values that I'm plugging in. Because it's never fun to plug in values that we can't take the square root of nicely. So I'm actually going to stick to perfect squares. So for t, I'm going to jump around a bit. I'm going to start with 0, seems fine, and then I'm going to go to 1. And then I'm going to do 4, and then I'm going to do 9, and then I'm going to do 16. And you probably have a good idea as to why I'm picking these specific t values, just so it'll play nicely with that square root. I'm just trying to get some points to plot so that I can get some faithful representation of the curve. Now if I go and find x first, I'll say, well, if x is square root of t, then when t is 0, we get square root of 0, which is 0. When t is 1, we get x is square root of 1, which is 1. When t is 4, we get x is square root of 4, which is 2. And of course, I'm just going to generate these integers increasing by 1, since that's how I kind of picked my t, as the perfect squares in order. So square root of 9 is going to give me 3, and square root of 16 is going to give me 4. And then I can work with y. And we're going to see something interesting happening with y because we jumped around so much on the t values. Even though y moves linearly, it's going to be not really appearing that way in my table since I'm jumping around my t values. But if t is 0, I get 3 minus 0 gives me 3. T is 1, I get 3 minus 1 gives me 2 for y. T is 4, I get 3 minus 4 gives me negative 1. When t is 9, I get 3 minus 9 gives me negative 6. And then when t is 16, I get 3 minus 16 gives me negative 13. And now I have these ordered pairs that I can work with. And I can write them out as ordered pairs. We have x comma y, so we have 0 comma 3, 1 comma 2, 2 comma negative 1, 3 comma negative 6, and 4 comma negative 13. These are the points that I have to plot. Well, let's see if we can get a graph going here, right? The x and the y-axes. And it looks like x only goes so far out as 4, so I'll just make sure I have enough for that. 1, 2, 3, 4. And I'm maybe going to have to exaggerate my scale a bit in the y direction to make sure everything's going to fit, because I got to go all the way down to negative 13. So we'll do negative 1, negative 2, negative 3, negative 4, negative 5. I'll label that. Negative 6, negative 7, negative 8, negative 9, negative 10. I'll label that. And just a bit more. See if I can fit it. Negative 11, negative 12, negative 13. Good enough, right? I'm trying to get some rough sketch here. And I can start plotting points. Well, let me get a scale up in the y direction. I'm going to need that as well. So positive 1, positive 2, positive 3. Looks like what I'm going to need. Should be good to go. Should be all right. So I have 0, 3. So that means I want to 0 in the x direction, so right in the middle, not moving to the left, not moving to the right, but then up 3. So I can plot that point. Then I have 1 comma 2, so x is 1, y is 2. I can plot that point. 2 minus 1 is now underneath the x-axis. And then 3, negative 6. So maybe better to go to negative 6 here and try to safely travel out. Not easy to do with the stylus, but he's doing the best he can, folks. And then 4 for x, negative 13 for y. That brings me pretty much all the way down to the bottom. And then connecting with a smooth curve. Oh, well, gotcha. Let me get a curve that looks like this. Should look a bit sort of more nicely rounded with a very pretty concavity to it, but what can you expect with the stylus? And I did plot these points in order, right, starting with when t was 0 and then going through to when t is 4. So I want the arrowheads indicating that direction this curve is falling. Looks reasonable. It gives me some rough ideas as to how the curve is going to look. Now I would like to eliminate the parameter t and try to work with some Cartesian representation. Now I can do this. Let's go back. So I changed this. We did x's square root of t. Y is 3 minus t. Now, like I was saying before, it looks like one of these is actually easier to manipulate. So if I started, I could actually start working with y. I could say, well, y plus t is equal to 3. So then it follows that t is equal to 3 minus y. And with that in mind, I could say, well, x is square root of t, so then x is the square root of 3 minus y. Gives me a really good representation of this same function, but in a Cartesian manner. Now, I'm not trying to be hesitant of working with the other way to go about it, and maybe we prefer y as a function of x. That's something that seems a little bit more normal to us in calculus. I can do that, but I have to be careful. I have to be thinking about what's happening. So if I wanted to try the other way of doing this, quote unquote, I could actually solve for t starting with x's equation, and to do that, I would have to square both sides. So we'd say, okay, well then t is equal to x squared, and then I can substitute this into y and say, well, if y is 3 minus t, then y is 3 minus x squared. But there's a bit of a problem with this. And if I look at this, I'd say, well, that makes sense, right? 3 minus x squared would be a parabola opening downward, and then it'd have that nice sort of vertex up at 3 on the y-axis. That's not what I quite have, though. I don't have that entire parabola. So there's something that I want to make sure, well, it doesn't look great. It looks kind of sickly, but I did my best. We want to think about what sort of happened, something that we overlooked here. When we plugged in values for t, those values had to be non-negative. I could pick 0, I could pick positive things for t, but nothing negative because I was taking a square root. I didn't want to leave the real number system. Not today, anyways. However, there's a result that happens because of that. That means I'm only going to get non-negative things out for x, right? I can take square root of 0 and get 0, or square root of something that's positive and get something positive out. If I think about how the square root function looks, it's kind of stuck to 0, 0, and then quadrant 1. So what we're noticing is that since t, so I can make sort of a little comment here, since t has to be greater than or equal to 0, it follows that x has to be greater than or equal to 0. And that's the restriction that I want to keep in mind. So here I'd say, well, yes, y equals 3 minus x squared is reasonable. It's fine to say that. But there's more to this in that x has to be non-negative. X has to be greater than or equal to 0. So this is another way, perhaps a bit more of a familiar way, I could represent this. But I have to be careful. If I'm doing something a bit more dangerous to eliminate the parameter, I want to make sure that I'm getting the full story. Whereas if I do something a bit safer, I might not have a function that looks quite as nice, but should be still a very reasonable way to write it. So up to you, think about it. Let's talk about section 10.2, where we have calculus with parametric curves. We'd like to find the equation of the tangent to the curve at the point that we're given with the parameter that we're given here. And let me actually modify this one too. I'm going rogue all day today, all day every day, but especially today. I'm going to change these curves. Here I'm going to let x be t cubed minus 1, so I'll change the sign. And I'll change the sign in between the other one as well. I don't want anybody to feel left out. So we'll do y is t to the fourth minus t. And we'll keep the point the same. We'll do t equals -1. Now, finding the derivative with parametric curves, it's interesting. There's something that we probably wouldn't quite feel as intuitive if we didn't see it before. Now that I have x as a function of t and y as a function of t, there are a couple of things I could find very easily. I could find dx dt, taking the derivative with respect to t. I could also find dy dt. But what I would like is I would like to find the traditional derivative, the Calc 1 derivative, as it were, dy dx. I'm always interested in this because I always want to know, what is the derivative of y with respect to x. And I want to think, well, how can I find these pieces using the parametric equations? Like we saw in the previous examples, we could try to eliminate parameter t. And if I'm able to write my equation as y equals some function of x, then I can differentiate it no problem. But maybe I'm not always able to do that. Maybe I can't always eliminate parameter t, and I want to try to find a way to work with that parameter. And here's where chain rule really comes in to help us. We could say, well, if I want, I could find dy dt by using chain rule. We could say, well, this is going to be dy dx times dx dt. And this is just a traditional Calc 1 variation on chain rule. We'd say, well, the dx is kind of canceled. There's more to the story than that. We know that. But we were essentially saying dy dt equals dy dt on both sides. But so what's nice is that with this representation, I can actually solve for dy dx. It looks like all I have to do is divide by dx dt. So we'd say, okay, well then dy dx, my Calc 1 derivative, is dy dt divided by dx dt. And of course, there's a bit of a restriction that we're now placing on this. We're saying dx dt should not be 0. If it is, we have division by 0, so that would be an issue. But otherwise, we now have a way that we can represent dy dx. It's dy dt divided by dx dt. I want the ratio of these derivatives. And now I can find dy dx in terms of parameter t. I want to work with parameter t. I don't want to fight against it. I don't want to ignore it, pretend like it's not there. I want to be able to work with it and to be successful in life. So let's go ahead and find these pieces. We said x is t cubed minus 1. I'll rewrite it because I don't have a great memory. And y was it t to the fourth minus t, t to the fourth minus t. See? Getting better every day. We can find dx dt. Not so bad, right? Derivative t cubed is 3t squared with respect to t. Derivative minus 1 is 0. So I have that piece. Derivative of y with respect to t, dy dt, gives me 4t cubed minus 1. Derivative of t is 1 with respect to t. And then I can assemble my derivative, dy dx. That's dy dt should go on top, so that's 4t cubed minus 1. Divided by dx dt is 3t squared. And this is what we're interested in. This is my derivative, dy dx. I'm going to make that 3 look a little bit better. My 3's never look great. Now that I have my derivative, dy dx, I can think about what the question is asking me to do a bit better. It wants me to find the equation of a tangent line. It gives me the value t equals -1. So what I can do is I can say, well, hold on a second. I have the derivative dy dx. My slope for my tangent line is going to come from my derivative dy dx evaluated at t equals -1. So let's find the slope, just like we would have done back in Calc 1, but with an added twist. If I plug -1 in for t, I get 4 times -1 cubed minus 1 divided by 3 times -1 squared. And so how is this going to look? Well, -1, if I cube it, stays negative, stays -1. 4 times -1 is -4 minus 1 divided by 3 times -1 squared. That's 3 times +1. We'd say, well, here -4 minus 1 gives me -5 divided by 3. So my slope is a -5/3. Also, I want to find x and y. We have that x is equal to t cubed minus 1. Y is t to the fourth minus t. And I want to plug -1 in for t. So I say, well, I'll plug that in. I can find my point just by plugging that in. So if I plug -1 in for t, I get -1 cubed minus 1, which is -1 minus 1, which is -2 for x. And I can do the same for y. If I plug -1 in, get -1 to the fourth minus -1. Since I have this even power, that's going to give me 1, and then plus 1, so that gives me 2, positive 2 for y. And now I have all of the information that I could dream of. Remember, my slope was -5/3. And then I have this ordered pair, x is -2, y is +2. Now I have all of the information I need to build the equation of my tangent line. I have my tangent slope and then a point that should be on there. So I want y minus the y value equals my slope times in parentheses x minus the x value. Let's plug everything in. So I get y minus 2 is equal to -5/3 times in parentheses x minus -5/3. Sorry, whoops. Who's watching? Who's watching me? I'm staring at the slope. The x value is -2. Sorry, x minus -2. There we go. So we got y minus 2 equals -5/3 times in parentheses x plus 2. And I can distribute into the parentheses. Of course, I want to do that. Y minus 2 is equal to -5/3 x, and then minus 5/3 times 2 gives me 10/3. And then I just want to add 2 to both sides, solving for y. So y is equal to -5/3 x minus 10/3 plus 2. And I should get a common denominator here. So -5/3 x minus 10/3 plus 2 is really 6/3. If I multiply it by 3/3. And then I can add these constants together. So we get y is -5/3 x, and then minus 4/3, right? And I have this nice slope-intercept form of my line. And there's my tangent line that I was looking to find. Let's take a look at this next question. I want to find the first and the second. Hey, the second order derivative. And then I want to answer the question, for which values of t is the curve concave upward? I'll just leave this one as it is. We have x is t minus ln t, y is t plus ln t. And I want to start by finding dx dt and dy dt. Derivative of x with respect to t, derivative of t is 1, minus derivative of ln t is 1/t. And then finding dy dt, derivative of t is 1, plus derivative of ln t is 1/t. And remember, we can find dy dx by just assembling dy dt divided by dx dt. So we'd say, well, dy dt is 1 plus 1/t, divided by dx dt is 1 minus 1/t. And I maybe wouldn't want to leave it quite like this. We could get a common denominator. We could also just work with multiplying by a clever form of the number 1. Let me actually get a common denominator here. I think it's going to be helpful later on. So if I get a common denominator, I would have t/t plus 1/t divided by t/t minus 1/t. And this is going to give me, in the numerator, I can write this as one fraction, t plus 1 all over t, divided by, in the denominator, t minus 1 all over t. And then we'd say, well, don't divide a fraction by a fraction. Don't ever do it. Multiply by the reciprocal instead. So we'd say t plus 1/t times, if I flip the fraction on the bottom, I get t over t minus 1. The t's are going to cancel across the fractions, so I'm left with t plus 1/t minus 1. And that's my first order derivative dy dx. Now from here, the question asks me to now find the second order derivative, Let's talk about second order derivatives. So if I want to find the second order derivative of y with respect to x twice, the way I would want to do this is I would want to find the derivative with respect to t of dy dx. And I think that makes sense. We think of a second order derivative, we think find the derivative and then differentiate again, but there's a bit more. I want to then take this result and divide it by dx dt, whatever that was originally. And this is easily overlooked. We'd say, okay, I have the first order derivative. If I want a second order derivative, I should just differentiate again. That makes sense, right? That's a normal inclination for us. But that's not quite how it works with parametric curves. Remember, the first order derivative was a bit involved too, different than maybe we would have expected. In order to get the second derivative, I want to then divide that by dx dt. That's all I have to remember. That's the only sort of extra piece that I'm going to need to work with. But if I can remember to redivide by dx dt, then I should be good to go. So okay, so let's start with the piece that sort of makes sense to us, which would be differentiating this expression that we have for dy dx. I want the derivative with respect to t of t plus 1 over t minus 1. And I'm just going to use quotient rule. I want to rewrite the numerator, I want to rewrite the denominator up in the numerator of my derivative. So whatever the denominator is, write that up top first, t minus 1, times the derivative of the numerator. Derivative of t plus 1 with respect to t gives me 1. I want to subtract away from this. Now I want to do the opposite. I'm going to rewrite the old numerator, that's t plus 1, times the derivative of the denominator. Derivative of t minus 1 gives me 1. And then this is all divided by the old denominator squared, t minus 1 squared. And I can clean this up. Multiplying by 1 doesn't really do much. I can distribute the subtraction in the numerator. I get t minus t and then minus t minus 1. So t minus 1 minus t minus 1 all over t minus 1 squared. T minus t is going to cancel. I'm left with negative 1 minus 1. So here I get negative 2 over t minus 1 squared. But this isn't quite the end of it. Now what I want to do, so this is an important result, we might want to circle or square it, but to find that second order derivative, I want to take this result and I want to divide it by dx dt. And this is why I was a bit careful with how I manipulated this. Dx dt is 1 minus 1 over t. I did get a common denominator, and I did write this as one fraction. So I'm going to use this version of it. If I had done something like, let's say at this stage, multiplied by t over t, it would have changed. It would have been okay for this part of the problem, but it would have changed dx dt. I would have to go back to this version of it. Since all I did here was get a common denominator, those are kind of safer moves. So this is still the same dx dt, just written as one fraction. T minus 1 all divided by t. That's what I need here. T minus 1 all divided by t. And that should be dividing what I just got when I differentiated my first derivative with respect to t. Well, okay, we would say don't just leave it like this. We want to multiply by the reciprocal, so I can do negative 2 over t minus 1 squared. But then I want to multiply by, I want to flip this, we'll do t over t minus 1. And I can actually combine these pretty nicely. So let me write it down here. We'll say the second order derivative is going to give us negative 2t divided by, I have t minus 1 cubed. And this is our second order derivative using that new parameter t. Now there was one last piece to this question. It says, for which values of t is the curve concave upward? So what we're essentially saying is concave up when the second order derivative is positive. And the way that I want to do this is with a sign chart analysis. So I want to find when my second order derivative is 0 or undefined. I want to try to find the critical points of my second order derivative. So say second order derivative is 0 when t equals 0 and is undefined, that means a 0 in the denominator, when t is positive 1. And I'm going to use these values to break up a number line on t, and then sort of work from there. So I'll say, well, let me get my number line. I'll sort of place these in order as they would appear from left to right. 0, 1, and I'll get some reminder of what my derivative, my second order derivative was, so a bit closer. Negative 2t over t minus 1 cubed was my second order derivative. What I'm going to do is I'm going to pick test values in each of the regions. So something smaller than 0, for example. I kind of want to be, I could be extra critical about what's happening here and say that some of these values don't really make sense. For example, 0, I couldn't plug that into the log function, right? So it wouldn't make sense for x or y. So probably not even worth really exploring. But anything greater than 0 is fine. If I still want to work with the same sign chart, I could still entertain these values, but I do want to keep in mind some restriction with the original problem. So I think it's worthwhile to point out at this point, hey, 0 doesn't really make sense for t, because for us to have t equals 0 would actually interrupt how we've defined x and y, which is a problem then. It's undefined for x and y, so then there's an issue. And everything else would be fine, though, everything to the right here. So if I want to test this region, I still can. It's actually not going to give me an error in this case just by happenstance, but it's probably not even worth our time to explore. So I'd say, well, maybe skip over this then. And this critical value of 0 is suspect as well, but I'm still going to consider things to the left and the right of 1. But otherwise, if there wasn't some restriction with x and y, I would likely want to test this region. But let's say, what about between 0 and 1? Something less than 1 but greater than 0. I would pick 1/2. There's other values that would work. I'm not going to go crazy. And then if I want something greater than 1, I'm not going crazy there either. I'm going to pick 2. Born to be mild. And I want to plug these in to my second order derivative, and I just want to know, is it positive or negative? So if I plug 1/2 in, negative 2 times 1/2 divided by 1/2 minus 1 cubed, I don't really care what this numerical evaluation is. You could have picked a test value of 1/3 or 1/5 or anything different. You'd get a different number, but the sign of that number would be the same. So if I go here and determine, well, if this is positive or negative, let's look at what happens in the numerator. A negative times a positive is negative, divided by 1/2 minus 1 is negative. A negative number cubed is negative as well. Negative divided by negative is positive overall. What if I plug in 2? If I plug in positive 2. So that's negative 2 times 2 divided by 2 minus 1 cubed. And so what about this in this case? Negative 2 times 2, it's going to give me something negative on top, divided by 2 minus 1. It's going to give me 1. If I cube it as 1, so that's positive. Negative divided by positive is going to give me something negative overall. So okay, so this is what we're looking at. And I want to know where we concave up. Concave up means the second order derivative should be positive. And we found where that is. Right, that's going to be here, less than 1, greater than 0. So in this interval. So we'd say concave up when t is in the interval from 0 to 1. And there I have the rounded parentheses there to not include the boundary. We'll take a look at one more example, and then that's going to be it for our daily problem set today. I want to find the points on the curve where the tangent is going to be horizontal or vertical. Here I'm given x is e to the sine theta, and y is e to the cosine theta. Now there's nothing really special about parameter t. T is a common sort of nomenclature for these parametric equations, but there's nothing special about t. It could be of any other variable, and we would still regard it the same. So in this case, if I want dy dx, well, I'm going to want dy d theta divided by dx d theta. Okay, not so bad. And I can find dx d theta and dy d theta. Here I just want a bit of chain rule. Derivative of e to the sine theta is e to the sine theta times the derivative of the exponent, which gives me cosine theta. And for dy d theta, remember the derivative of e to the stuff is e to the stuff. That's my outer derivative. Looks the same. But then I have to multiply by the derivative of my inner function. Derivative of cosine theta is negative sine theta. Now I can assemble that derivative, dy dx. Say, well, dy d theta should go on top. I'm going to bring the minus sign in front. We'll do minus e to the cosine theta times sine theta, divided by dx d theta, which is e to the sine theta, times cosine theta. And this is my derivative, dy dx, my first order derivative. Now I was asked to find points on the curve where the tangent is horizontal or vertical. Now let's break these up into two separate possibilities. I'll do h for horizontal, I'll do v for vertical. Now for the tangent line to be horizontal means the slope of the tangent line would have to be 0, which means that dy dx would have to be equal to 0. Whereas for the tangent line to be vertical, the slope would be undefined, which means that dy dx would be undefined, of course. And let's go ahead and we'll start with working with the horizontal points of tangency. For my derivative to be 0, and important to notice that my derivative is a fraction, it's a rational function. For a fraction to give me 0, I want 0 in the numerator and not in the denominator. So we'd say I want 0 in the numerator, so this means I want negative e to the cosine theta times sine theta to be equal to 0. Just setting that numerator, I'll jump back to it, setting that numerator equal to 0. And the exponential function will never be 0. The minus sign can be divided over, so really we're just focusing on sine theta in this case. This all reduces to sine theta should be 0. And well, when is this going to happen? Well, there's lots of values that will work for theta, but we don't really need the repetition so much, so we just maybe think of the first couple of values that would work, and anything else would just sort of double back up on the same information. So we'd say this is going to work when theta is 0 and when theta is pi. It's also going to work for 2 pi, 3 pi, any integer times pi in this case. But any excess information isn't going to give us new details about this. So I'd sort of leave it here. Similarly, we can talk about the vertical points of tangency. We say the slope or the derivative has to be undefined, which means I want division by 0. So now I'm focusing my attention on the denominator, that the e sine theta, so e to the sine theta, times cosine theta would have to be 0. We said the exponential function isn't going to be 0 on its own, so the 0 must be coming from cosine theta. So cosine theta must be 0, which means that theta would be pi over 2 or 3 pi over 2. And then, of course, 5 pi over 2 would work, 7 pi over 2, but we don't probably need much more than this. Something to consider, the question asked for the points on the curve, so I should really be finding these as ordered pairs. So what was x, what was y? X was e to the sine theta, and y was e to the cosine theta. And we can start with theta is 0. When theta is 0, I get x is equal to e to the sine of 0, which is e to the 0, which is 1. And y would be e to the cosine of 0. Cosine of 0 is 1, so e to the 1, which is e. So this gives me an ordered pair. This gives me the ordered pair 1 comma e. And I could also take a look at when theta is pi. I get x is e to the sine of pi, which is e to the 0, which is 1. And y is e to the cosine of pi, And cosine of pi is -1, so e to the -1, which I could write as 1 over e. So I get another ordered pair, x is 1, y is 1 over e. So these would be the 2 points where the tangents are horizontal. Now if I went on, let's say I did 2 pi next, it would just churn out this same point, 1 comma e. It wouldn't give me any new information, because sine of 0 and sine of 2 pi are the same. Cosine of 0 and cosine of 2 pi are the same. So it wouldn't really give me anything new to work with. Let's talk about those vertical points of tangency. If I start with theta is pi over 2, and say, well, x is e to the sine of pi over 2, which is e to the 1, which is e, and y is e to the cosine of pi over 2, or that's e to the 0, which is 1. So I get the point e comma 1 as a vertical point of tangency. And then I can work with the other value for theta was 3 pi over 2. Let's say, okay, well then x is going to be e to the power of sine of 3 pi over 2. We'd say, well, that's e to the -1, which is the same as 1 over e. And that y is e to the cosine of 3 pi over 2. Cosine of 3 pi over 2 is 0, so e to the 0, which is 1. So we get this other ordered pair, x is 1 over e, y is 1. And that would be for the vertical points of tangency. Try to get them all in the same view. So here we have 2 points of horizontal tangency, 1 comma e, 1 comma 1 over e, vertical points of tangency, e comma 1, 1 over e comma 1. Hey, thanks so much for spending your time with me. If you made it all this way to the video, make sure you say something cool about yourself in the comment section below. Let me know what you're up to. Let me know how you're doing. Hope you're enjoying your day. But remember, no matter where you are and what you're doing, keep learning, keep dreaming, and always follow your heart. And I'm going to see you soon for another one of these daily problem sets, so don't go anywhere. We'll be right back. Until then, take care.